Hello there. Welcome to another problem session. This actually is a little bit advanced problem and pretty interesting. You don't find this problem in a lot of the books that should have this problem. So here is a solenoid. So this is a very long solenoid. So you can assume this to be, it can assume to be very long. Radius is r, and current is when current is flowing. So you might say this whole thing is in vacuum, if you prefer. So there's no like air pressure, things like that. That's just a pressure is going to come from just magnetic field. So when the current is there, you already know using right hand rule. There will be magnetic field inside, and it's going to go on and kind of wrap around like that, and there will be magnetic field. I should be straight that way, and magnetic field pretty straight in the solenoid. In the solenoid is very straight. So this is this magnetic field, and it's given by this. Now this you can derive using Ampere's law, and we did a video on that some time ago. So we want to find pressure. So if you look from this angle, you'll find that you have a circular thing. This looks like circular, and the current will go around here, and you have a so you have n times L loops. Each one of them look like this. So we can assume that the loops are so tightly wound they're just stacked on top of each other and pretty much continuous. Current I is going around it. Okay. What will be the pressure over here? That's the question. How do you answer questions like that? Well, the pressure will be all like pushing outward. Pressure will be pushing outward on this. So one way to, if the pressure is P, it will be pushing on all the wires outward. Well, there is a method of finding, working out statics, in statics, where the question is when there is a static equilibrium, how do you find a force? All the forces are balanced, right? So how do you find the force? One way is just look around and all the forces, try to find all the forces and balance it. There's another way, it's called a method of virtual work. So you imagine that this thing is going to become pressure is going to push out. It's not pushing this out, but there are things which is balancing it, right? So there are other forces balancing it. So rather than look for the other forces, we just work in the energy space, work in energy, and that's much easier to do. And so we imagine what will happen. So this is the radius r, and from this we want to increase the radius by r. So this was the r, and then we push it out to a radius r plus dr. So what will happen is, if you were to push this out, you can see that this pushing out is going to be, now there will be magnetic field was going through this area. Now it's been going through this bigger area. So magnetic flux will increase, right? And magnetic flux increase, which also mean that you will induce current in the opposite direction from the back EMF. So there will be like a back EMF. There will be current delta I in the backward, but I want to maintain current at I, which means the source will have to, balance out that current used to produce I. They have to produce a little bit more current to balance out the induced EMF current. So this is one source of energy when you push it out. So that means a source, in order to maintain current through solenoid at a steady value I, will have to supply extra energy. That extra energy will be this back EMF. This will be delta I induced, and this also due to EMF induced, and EMF induced is d phi dt. So energy, and this will be EMF has this will be equal to that energy, right? We can try to figure that out. So let's say this be some kind of W. Let's unit rather than use E, which is like electric field symbol also, we're going to use W for energy. So this is the total energy supply. Where does the energy go? Well, it goes into, you can see over here, magnetic field. Now, because this is going to be same current was I. This will be same current as before because of this. So I'm not changing current, but you can see the magnetic field had energy up to inside earlier, right? Now you have extra areas through the flux goes, and so there's extra energy. So there will be some energy goes into dW magnetic energy, and we have done a video on magnetic energy, okay, and we'll use that. And then some of the energy will have to go in when this pressure is doing the work. So work done by pressure, so we'll have a pressure times, we'll take a area of this, and then pressure times area will become the force, and I'm going to push it outward, so that will become force times distance. That will become the work done, and we'll call that mechanical work. So this work by expanding, that will be d mechanical work, and this is where the pressure will be. So we'll have depend on pressure. So now we'll have this expression, how much energy, that extra energy that my source will have to supply due to back EMF, due to this back EMF. So that's this stuff, and that goes into this plus this. So we'll have a formula like W equals to D, let's call it dW. dW is dW towards magnetic plus dW mechanical, and this has a pressure in it. So this will have an equation with P in it, and everything else will be known, then solve for P. So that's going to be my strategy. We can do a very similar problem. If you want to go ahead and do this, and go ahead do this and then come back and see my solution. But meanwhile, I'm going to say there's a very similar problem. So like this capacitor, parallel capacitor, and there's only electric field between them. So this is a plus and this is minus, plus sigma minus sigma, and the area is A and the distance is D. So your question can be, what's the pressure on the plates? And that will come from the electrical field that lies between them. You can imagine this is a vacuum here, and so it's not coming from vacuum, but coming from electric field is actually pushing on the on these plates. Okay, so this is also a very similar problem and can also be done by virtually making this distance go a little bit bigger. And so you have the original capacitor, and then you have a capacitor that's that distance apart, and then you say, if I have a if connect to a battery, this battery will have to provide energy for extra electric field energy and mechanical energy, and then from there you can figure out the pressure formula. Okay, let me go back to this over here. You will find, so if you go and do it, you will find that pressure is equal to 1/2 mu naught B in square. B in, of course, is mu naught N, mu naught Ni. So that is going to be like that, and we'll work it out in the rest of the session. Okay. All right. So let me erase and get myself some clean space to work with. All right. Okay, so let's work out dW magnetic. Okay, so we can just say what's the magnetic energy here. So start from magnetic energy in the original one, get an expression for that. So magnetic energy density, so let's see, magnetic energy density will be 1/2 mu naught B. Let's B in, inside there is B in, so B in is square. This is the density times the volume. The space is how much volume there is. Well, you have a pi r square times L. So that's the volume in the space. So this is the density, this is energy density, and this is the volume. And the density being constant, just have to multiply, don't have to integrate. So if I do dW, the only thing that I want to change in this is R. So everything is constant here. So dW will be dWm will be dWm over dr times dr. And so taking this derivative, multiplying dr, you can see that 1/2 mu naught, and B in is just mu naught Ni square for that. Then you have a pi, and let's write down L here, and it's going to be 2 times r dr. This 2 cancels out. This mu naught will cancel one of the mu naught, so it's going to be mu naught, and you have n square I square, and there's a pi here, LR dr. So lots of symbols here. Okay, it's easy to get lost. So if you get lost when you're doing it, don't worry, this is a common problem here in this problem. So we got this part. Let's look at the mechanical work. Well, so as I was saying, think about this as a cylinder and look at this patch. And so this area will be dz, and from here you can see this whole area, you can just do the entire area. So let's look at the entire area, just this whole surface area. So surface area, so force that's acting is pressure times entire surface area, and force is just everywhere outward. So this is the radial force acting outward, and pressure, so you have a 2 pi r L, 2 pi r L, so that's F naught, and then if I push this out, Fr, this Fr dr, that's the magnet. This is the mechanical work. So this is going to be just 2 pi times pressure times L times R dr. So this one done. Well, what's the back EMF going to be like? Okay, so this will come from the battery. You know, this thing is connected to, so this wires, actually the current is coming from somewhere, right? And current is going, so some battery is going to have to keep the same current. So what's the back EMF? Back EMF is the amount of energy per unit charge that it has to supply, right? So back EMF will be d phi dt, and so when we multiply it with this EMF, and then let's see, so how much energy, I need to convert this to energy. So this is the EMF, and the current is at I, maintaining at I. That means the extra power needed will be this time this voltage times current. So d phi dt times the current. So that's the extra power needed, and this is power. So if I multiply by dt, then that will mean extra energy. That's this stuff by battery, by source, will be I times d phi. Also, I need to figure out what the phi is. Well, phi is the magnetic field flux through this thing, right? Through this thing. So if you look at phi through one loop is B in times pi r square, but we have number of loops is n times L, that many loops, this many loops per unit length and this length. So this is phi equal to n times L times n times L. So this will be the phi. All of these guys are independent of R, and R is the only one that I'm pushing. So d phi will be I times NL B in times 2R dr. So now let's write the B in. B in is mu naught Ni. So this is for the W. So we have a 2 times mu naught N square I square LR dr. You can see this is the same expression as that. Looks like half the energy goes towards magnetic energy, and other half energy goes towards the mechanical work. So now I can say, use this equation, I can and set up the equation and then solve for it. Let me erase and kind of clean up some space here. Okay, so first thing to notice is we have a dr in each of the expressions, so we can just drop dr. So we have and this one, well, let's write this equation: 2 mu naught N square I square LR dr equals to this whole I think I forgot to copy this pi. So there's a pi here, and so there's a pi here, so there's a pi here. So this guy is a pi mu naught N square I square LR dr, and then you have a 2 pi PLR dr. I hope I didn't make any mistake here. I know this is a problem in this big thing, so these r's all cancel out, and L must cancel out from every one of them. This pi cancels out from all of them, and this actually is same as that, so it's going to subtract, and so the P will be so this will all become 1 here, and so you have a P equals to, and then you have a 2P here, so 2P equals to mu naught N square I square. So if I do 1 over mu naught, make it mu naught square, then this is the B. So this is the B. B and B in is same as B. There's no other magnetic field here. So we can, and this 2 can come down here. So P equals to 1 over 2 mu naught B square. Okay, so I don't know, earlier I probably remember wrong. I think this is correct answer. This is the answer. I think I may have written half mu naught B square earlier. This is not mu naught, it's just at the bottom here. Okay, if you remember, this is actually the same expression as the expression for energy density. See this? Energy density and the pressure is actually same formula. And you should expect very similar thing to happen in the parallel plate thing. And I'll just leave that as an exercise. You should try to figure out pressure between two parallel plates, two charged parallel plates. And so that question that I pose to you again. In the case of parallel plates and with electric field E, and the question is the pressure equals to, this is the question to you, 1/2 epsilon naught E square. Okay, that's the teaser for you. Maybe you should try to do it yourself. Okay, with that, I would like you to subscribe to this channel. It really helps the channel grow. A lot of people are subscribing, and I really appreciate it. And you can also hit the like button if you like this kind of problems. There's a whole bunch of similar problems done in physicsbootcamp.org. That's the website that I maintain. Okay, that's enough for now. Take care and bye.